He mentioned a little bit about philosophy, and he mentioned about technical, and he also mentioned about business. So I'm going to have all three of them. Okay. So I hope that it is interesting, because this talk is actually going to summarize a large. It's actually about 25 years of actually effort, basically influenced by academia, and then influenced by industry, and after that again academia. Okay. So what am I going to talk about? I'm going to really talk about actually where AI is, and there's a lot of talk about actually explainability, inspectability, safety, and how we can handle the complexity. So this is basically where a lot of let's say there's a lot of promise in AI, but then the question is, can we actually deliver? And I'm going to basically paint a picture which actually shows that what we talk about AI, when we talk about AI here, it is not actually a revolution, but it's actually an evolution. That's number 1 point. And the number 2 point that I want to make essentially is that explainability is something that scientists have been thinking about for a long time. It is not something new. That's number 1. And in the very hardcore system science people and engineering people have been actually thinking in terms of models of complex systems and how to actually predict performance and how to validate these systems. The biggest issue that has actually been daunting them or challenging them was actually the level of scale. They haven't had the chance to actually validate their ideas in large scale, in big data settings, and in large scale, let's say, validation facets. So effectively, the point is that actually science has been evolving in its own pace, and there has been actually systematic efforts over the years. And the biggest jump is since 2012 was this deep learning jump. And the point I'm trying to make essentially is that machine learning has already been making progress since the 2000s. And then in 2012 there was this leap because of the fact that a lot of people realized it, and also the performance went up when you use billions of samples and then train these things. And so computation helps you, platforms help you, and then performance obviously went up. And since there is empirical success, there is basically feedback into essentially now science. So that's the way I see it. That doesn't mean that actually we don't say that the big leap that happened in 2012 is anything small. What we're saying is that at that time what happened is that the confluence of multiple factors, like the computing, the algorithms, and the persistence of those people who've been pushing model data-driven science, has basically paid off. That's the way I see it. Okay. So what I would do essentially is talk a little bit about this background of how things evolved. That's the first step. And then I'm going to talk about essentially my own journey, which will give you a little bit of an idea of what is possible already in the 2000s, and also what was basically influenced before. And then the last part which I want to talk about is, okay, there's so much buzz about AI, so much buzz about data science, all this change that's happening. Now what does it mean for our kids? What does it mean for actually high school students? What does it mean for undergraduates and graduates, and for let's say business people? What does that mean? Does that mean actually we all have no jobs in 10 years or 15 years? Or what do we do? So that is basically my last part. Okay, so there is you may have seen this video from DARPA, very nice video, which talked about waves of AI. Now essentially what you see in this slide is okay, last 3-4 years, lots of talk about AI, AGI, superintelligence, ASI, and doomsday scenarios about what AI can do for humanity, right? And the beautiful books which I recommend heartily is the Sapiens book and the Homo Deus book, and then the follow-up book from Harari, and of course there is the superintelligence activity. Now, I basically have one of the biggest things that I did in the last few years since I joined Frankfurt was actually spent more time with philosophers. Okay, so because I started asking some more basic questions about what's going on here. And one of the philosophers that actually philosopher of AI that you may know is Professor Sloman. He's retired. He's actually in his, I think, almost 80 now. And I met him essentially, and I saw his papers in systems thinking, and I said, oh great, this guy is actually thinking really about system engineering, complex systems, how it links to biology. So I had a meeting with him, and we met in the airport in Frankfurt and then went to the conference in Greece. And I asked him, what do you think about AI? How do you define intelligence? And he said, I can't define it. I wouldn't define it. And then I kept pushing him. In the end, I said, if you want to force me, I'm going to tell you lazy productiveness. And then I turned to him and said, you mean productive laziness? That would work too, he said. Okay. But it's clear. Okay, this is actually, in my opinion, the shortest description of intelligence. Because effectively what it says is, as an organism developing in an ecology, or an ecological system, what you would like to do in order to survive essentially is to bring to bear your experience into any task you want to do, and then be able to achieve it with minimal energy. So that is why we have all this apparatus that allows us to learn and to adapt and all these complex things that's going on we don't fully understand. Okay, so that's a beautiful let's say start. Now as I said, AI has been around since the 50s, and initially there was a lot of buzz about rule-based methods and essentially theorem proving, logic-based approaches, and so on. And of course, it was applied in effectively expert systems in the 70s and early 80s. But then it was clear that the problem is that these systems don't essentially address uncertainty in reality. And so there's a problem with actually the representational scheme. It's good for certain things like symbolic theorem proving and so on, but not necessarily for handling real-world information. And how do you get the rules? It's another question. How do you update the knowledge base? How do you revise it? It's another question. So a whole range of questions which still exist right now for even the deep learning guys. Then of course there was actually AI winter, and that was actually, they say it's in the 90s when I was actually a PhD student. And now I understand why my advisor was actually pushing me to do quantification of performance. Okay, but essentially the idea was, hey, we know how to, humans can provide you skeleton designs. How does it behave? Can you characterize the behavior and performance of these systems? And in fact, if you look at it carefully, between 1991 and 95 or 96 are the best papers I've seen in systems perspective in AI. Especially because they were trying to address the fundamental questions at the time, trying to break in and understand how to quantify things in a formal way. As the Bayesian network stuff started in the late 80s, early 90s, the issue of invariance, the idea of invariance, how to use invariance properly in vision-like problems was at that time. And then the idea of actually how do you even do search, design a search was also something which was pursued at the time, and performance modeling was pursued. So and then in the late 90s, early 2000s, there was actually really statistical learning. So the neural network, in fact, when I joined Siemens in 1994, 95, already there was a learning department which was focusing on neural networks, applying neural networks, and so on. There was the early turnaround. And then by the time early 2000s, you already had a lot of, at least in industrial big labs, activities in machine learning. Okay, and of course, this became a boom after the big data era, and then the computation complexity can be tamed by using advanced computers. That's actually what happened in the late 2000s. And basically, recently, there is also discussion about, oh, I need context sensitivity in these systems. I need actually human-like performance. I need actually adaptivity. So that's essentially what the era right now is. At least this is where groups like DARPA is investing in this activity. Yeah? And by the way, context-based vision is something that was actually promoted in 1995. And actually there were workshops in 1995 from SRI, Stanford Research Institute. So it is not a new thing. The only thing is that now we have alternative views of how to think about representation, how to do modeling, how to do analysis, and how to bring it together into a system. Of course, the scale of these systems have gone up. Okay. So the key point is, the nice summary from DARPA essentially is that these early waves of AI, they addressed essentially rule-based systems, and after that the statistical learning, which is the neural networks. And basically the main point here is that they do a lot less on learning and abstracting in the beginning. Later on, learning is increasing, but still the integration of all these perspectives including perception, learning, abstraction, reasoning, has not happened, right? And in fact, a lot of what you see, which is being exploited right now in the business areas, is the second wave and the neural network boom. Okay, and essentially, you know how this is working because you're all data scientists. You must be already using TensorFlow. So I skipped this, and of course, there is actually one of the big viewpoints that was also looked at in the last 2 years was, hey, look, this is really, it's all great. We can build a nice network and we can train it with millions of samples. I can scale to thousands of classes, classification. But you know what happens in a simple example where your child is holding essentially a baseball bat is the answer for something like this picture, right? So it's clear that statistically, overall, when you look at the population statistics on how the system is behaving, it looks good. But when you look at instances and then start analyzing these instances, it looks brittle. That's basically the message. The other problem, of course, is that when you have actually an original picture like this panda picture, add essentially certain kind of colored noise, then the human perceives it as the same, but the machine doesn't. So machine switches it. And this is basically what's called adversarial perturbation. And there are lots of papers that you know that's addressing this. And it's understandable because essentially these are living in high dimensional spaces, and it's all about the sampling, how you did it, and how you trained it. So that's basically it. It's understandable. So the DARPA and others are saying, oh, look, we need to do this in a context-sensitive way. We need to have actually machines that will perceive, learn, abstract, and reason, all using a central model. Okay. And in fact, they say, hey, okay, it also needs to explain why I'm making a decision. By the way, in this case, there's a cat. I want to be able to explain that it has a fur, whiskers, and so on. That's why I made a decision like this. Moreover, there are ways in which you can bring the specific generative process by which data is created to be able to do reasoning, understanding, and then learning with small number of samples. If you notice this carefully, the difference between these model-based perspectives and basically data-driven perspectives is that the model-based perspective puts in more inductive bias about the world and the way the world operates, bring it into a model, and then with a small number of samples you try to learn. That's basically the difference. This is actually the slide from Lake and Tannenbaum that explains how they think about probabilistic grammars and how it's used. Okay, so the key point is, what's the status now? The status essentially is that nowadays people talk about cognitive architectures. They talk about hybrid AI systems which combine actually deep learning, basically all kinds of architectures, attention with as well as reinforcement learning and so on, all sorts of integrated stuff. There is talk about predictive learning, meaning that you want to not only build an algorithm to produce an answer, but also you want to predict how well you are doing. And then you are working on basically scaling model-based systems by having probabilistic programming platforms, meaning that you want to write code in a high-level language. Underneath the hood, all of these things are basically translated into inference engine. Like I can specify what a traffic scene is, and I can specify how things are arranged according to a sensor model and actually according to a statistical model of the world. And then after that I say infer, and then that's it. Underneath the hood everything happens. That's at least what the idea is. So minimize the amount of programming automation tools that support this. And of course there's a lot going on in terms of end-to-end training, meta learning of architectures. You know about AutoML in Google and other type stuff. And there's a lot going on in adversarial networks, you know this. There's a lot going on in simulation reinforcement learning, you know this. And the biggest issue really is, can we take all these things and put formal, let's say, understanding on top of it? Meaning, can I talk about when actually I should apply what kind of tool, for what reason, and so on. So that's basically, by the way, in the last 2 years, lots of advances have happened. In fact, including how essentially you can think about all the sparse coding literature and how you can actually build sparse coding type of activities and link it back to deep learning. So there's very nice stuff going on. And in fact, there's a lot going on in what's called explainable AI. I've been looking at it closely in the last year. Now I find that, you know, okay, it's not bad, but there is actually things could be improved because I think they are just repeating whatever people have been doing before. Okay, so I just pulled up this slide from a business point of view and what business people are saying. For example, PricewaterhouseCoopers essentially says, hey, okay, explainability is all about understanding, reasoning behind each decision you make, having this transparency about what is going on inside this AI thing, and then how can you prove that essentially what you've done is correct. And by the way, how can you prove what you've done is correct? So it's a very challenging problem. In software engineering, it's been addressed by using formal methods. Basically, when you have logic programs and so on, you can talk about particular kinds of checking that you could do to make this happen, right? And but to do this for statistical things, this is a major challenge. How to do this for AI systems, it's still an open issue. How do you build simulators? How do you validate the simulators? How do you actually test offline and then bring it onto real world and do model validation is a major system engineering question, which you will see in the next slide. So now I switch. So I have now given you sort of an outline of what has been going on. Now let us just see how it parallels with some of my own personal experience. The first thing essentially is just to give you an idea of what you need, at least what I have done in order to become a systems person in this field. So what I have done essentially is learned undergraduate degree in electronics, then basically a master's degree in computer engineering, where I covered a variety of courses, including discrete math, abstract algebra, whatever you think about, including image processing, computer vision, AI, and so on. And then after that, theoretical computer science, followed by Bayesian statistics and system engineering. So that was my training. And look at the time period I spent, close to 13 years. Okay? And that's a large amount of time to build up a core set of portfolio and a diverse set of portfolio, all the way from conceptualizing something, abstractions, basically implementation, and then validation, and so on, and dealing with the complexity. That's basically one of the core things that I see one has to do if you want to develop this thing. I have a feeling that you can do this all not in 14 years. Maybe I was too slow. Perhaps you could divide by 2, 7 years. I think maybe not bad. Yeah. Now, if you can do that in 5, it would be even better if you can. But the point is that all of this thing, I had the opportunity to bring this into an industrial setting where there was a lot of possibility to really validate these principles in a corporate research lab. And that actually was in the next 10, 17 years. And then in around 2008, 2009, I just felt that there was something, there's an end to this. There should be a next level of scaling. I moved out. And then in 2011, I was here. And the last 7 years has been really about philosophy, psychology, neuroscience, and linking with system engineering. So who are the people who actually touched my, I can't really just enumerate everybody. All I can say is that there are some 3 kinds of streams of thought that has sort of influenced me. One essentially is basically my own advisor, Robert Haralick, who essentially is a pattern recognition Kingston Fellow Award. Basically, he's well known in image processing, computer vision, also in AI research. Then Tom Binford, who I was fortunate to be part of a committee together with him, and Haralick helped me be in that committee. And as a result, I learned a lot from Tom Binford, who was actually, I would say, he's one of the early people doing vision as a science. And then he's also known as a father of computer vision and model-based perception. And more recently, the last 7 years, I've been influenced by neuroscience and thinking in biology, and why actually the brain architectures could be actually paralleling what we are doing in software engineering, evolution, and system engineering. So just to keep it short, basically the principles I was learning in the university on how to think about formal analysis of systems was brought into applications and then developed into a center of excellence and then produced many systems. I don't want to go into a lot of this discussion, but here is what I wanted to do and play these videos. Unfortunately, there's a problem with the videos, but I'll walk through it at least to give you an idea of the kinds of systems we were building, just to give you a flavor of what is already possible in what timeline. Here is an example of a system. By the way, how many of you are from Cologne? So this actually is a system on the A4 highway that was done in 1998, 99. And in the A4 highway, what they wanted to do was they wanted to open up that lane, shoulder lane for traffic, because they didn't want to build extra highways. So therefore, they wanted to open up this thing for traffic. And the requirement in that system was that you need to be 100% detection and you have to be 0 false positive, because they try to detect actually pedestrians at a distance of 100 meters, and they want to actually use regular cameras, 4 cameras per PC, all sorts of requirements. How do you do that? Okay, and who actually went in and said I would do 100% detection and 0 false positive? Anyway, but that was the context in which I was thrust in, and maybe I'll play the video later when the discussions questions start. But the key point is, I want to just make a point about design, how we did it. We were able to get something like 98% detection, false positive 1 per day. Okay, on PC, which is nowadays at that time it was like 200 megahertz CPU with 64 meg RAM and 4 camera streams per PC. Okay, that's basically what we did, and the way we did it is the key. It is basically a system which was designed using context sensitivity. We used explicitly the knowledge about the world. So we used the knowledge about actually the fact that it's actually a traffic scene, the fact actually that it is a shoulder lane, the fact that actually traffic flows in particular, it could be in different directions, but it essentially involves particular types of structures. The fact that you might actually have changes, you're interested only in detecting the things in here, but what you are interested in to make sure that the false positive is absolutely 0. That means that you have to deal with weather, you have to deal with essentially rain, you have to deal with snow, you have to deal with actually minute variations due to jitter in the camera, all these constraints in the real world. So the key module that I had in that system, which I personally developed and I'm supported by other people in my team, was a function called cancel common effects. And cancel common effects was essentially my way of saying I taught her with the physics of the problem, wrote down exactly what the statistics of the image values would look like under the general world situations, and I propagated the world probability distributions down, all the way down to essentially the probability statistics in the ground, and then I asked the question, can I be invariant? How can I be invariant to traffic flow? How can I be invariant to shadows? How can I be invariant to lighting change? How can I make it so that it works the same day and night? And the simple answer was just use the physics, write down the math, figure out which variables you got to ignore, so try to find invariance for those things, and then figure out essentially what are your strong constraints. In this case, the strong constraints were the people sizes were constrained, the object sizes are constrained, therefore use that effectively as a way to check. That's it, very simple. What are the strong regularities? What are the invariances you need? Design a feed-forward system like a deep learning system. Just take the filters, cascade them, put it together, you get back a test statistic, and then you get a guess. And then the guess is actually you check over time using actually deliberation in the context. That's it. And in fact, that's exactly what's shown here in this diagram. It will come again, which is like the brain, essentially meaning that you have essentially intuition, which is using context sensitivity to quickly guess what the answer is, and then deliberation, which is actually improving on it. Okay, so to keep the story short, this kind of philosophy has been applied to many problems, and the key point is the system configuration is really nothing but different types of pipelines which are addressed based on this context idea, task and requirements, and there is a mapping from context task requirements to the solution. And in fact, the architecture we're talking about is basically something like what Daniel Kahneman talks about as system 1, system 2, and essentially hybrid designs, basically leveraging both model-based design and continuous learning, which you know. And the advantage of this is that if you do this in a context sensitive way, but then you basically cluster the context properly, you can then build a portfolio of solutions which address the issue of scalability, modularity, extensibility. That's what we did over 10 years. Yeah. So that's basically the in a sense what was done in this project. Essentially the process that we follow, thus, is start with the context, start with the requirements, have essentially a process by which the design is mapped to configurations, and these look like essentially dual systems. And then these dual systems can be analyzed using simulations or with the regular real data, check the performance, improve it. That's it. And if you do this regularly again and again, you see that you will have a portfolio of intelligent solutions. Okay, that's basically it. Now I'm going to say the last 7 years what we've been doing is link this philosophy to Christoph von der Malsburg's philosophy in brain sciences, and we've been looking at platforms for actual simulation tools. We've been building applications in the university setting, and then I'm trying to understand how to teach this to students. And essentially the main advance, I would say from my point of view, is that there is a way to link what we were doing in industry back to essentially the latest trends. And then I'll skip this, it's not that difficult. Let's just talk a little bit about education and then wrap up. So from an education perspective, as I said, you're going to see lots of things happen. Everybody's going to say, I have the new best thing. And I have this, I have that, I have this. You want to hear that. Every day there's something new. This is happening because it is natural, because it is actually, these tools are getting to work now and they're getting useful. So you need to be then effectively be agile. So you have to be agile. You have to be flexible. And you have to be able to figure out how to work in teams and make things work. That's the essence. From a point of view of businesses, it's more or less the same thing that what Boston Consulting is saying. Okay? And basically when I came in here in Frankfurt, I basically started, okay, this is what you need to do to address essentially this need that is coming out, that we need to teach people to think in terms of systems, think in terms of the model-based design, as well as data-driven design, combine it properly, and this is what we are doing. Courses like this, where we actually have basically 3 stream main courses, 2 semesters each. That means 6 courses really in some sense. Effectively, one is addressing this idea of philosophy and modeling. That's the first one. System engineering meet life sciences. It is basically about how systems can be formally specified, designed, analyzed, implemented, and also linked to biology and other things. Then the system engineering, software engineering 1 and 2 is really about software systems using platforms and working together. Then the third, of course, is the mainstream machine learning activities and how that's going. Notice that there is 1 and 2. 1 is foundations, and now 2 essentially typically is more complex later stuff. And then there is practice in machine learning, which can be projects. And then there is a seminar where we actually look at a whole range of things, including philosophy of AI. Okay. And here is a simple example of what one of the course looks like, and I'm done. The simple example is, here is the theme that's covered. So effectively, my point is, think in terms of what is the context, think in terms of what the task is and what goals you want. Based on that, think about what the design is. That's the first point. Then the next thing essentially is we teach them, okay, how do you think about what is context? How do you think about what's a task? How do you think about actually what is meant by performance? That's actually the next set of points. Then we ask, what is a learning program? So we think about programs with filters and combinations and with feedback and so on. And then we talk about where is the architecture coming from. And then after that, we have actually examples of things we've done before, and then things that are going on in the outside literature to basically give them a sense of how all this stuff works. So the key point is that in this modern era, there'll be a talk later about the democracy, liberal democracy. I think it fits in nicely. Basically, the point is that this essentially kind of work should be propagated to all levels, meaning that we need to have researchers who have systems thinkers and transdisciplinary thinkers, and then we need platforms which will address very core issues of how to structure these things so that people can work together with the machines to make systems faster and efficiently done. And then we need actually better training mechanisms for people who are already in industry and who can work together. And there is, of course, real projects, and there needs to be an integration of these perspectives. My son. So the key point that I'm saying is, whatever I was saying here, already Judea Pearl was saying. Okay. In fact, Judea Pearl has been, if you notice his work, he did actually heuristics and search in the early days. And after that, he worked on causality. He worked on actually Bayesian networks, actually. And then after that, causality. And more recently, he's been saying, hey, look, you think about intelligence in this form. You think about it as actually following things. You can do things by association. That's what he thinks his perception is, seeing. And then you want to do intervention in the world and things are changing, then you need to actually model causality, and you need to understand how the dependence of what the data is to my actions, and then you have to do the appropriate calculus to do interpretation. So that's basically his do calculus. And then counterfactuals. Humans always do that. Okay. So if you want to do all of these things, you have to really think about causality. So he says causality is more fundamental than essentially joint probability distributions, which most of the deep learning guys are doing. Okay. And this is a nice book. I haven't fully finished it, so I can't tell you everything, but at least I've read the parts that I felt I needed to read. So the main point I want to make there essentially is that this was in my breakfast table. I was talking to my son and my wife, and they were just saying, "What are you going to do for this other presentation?" And I was explaining. And then my son said, "Hey, Garfield said that." Okay, so that was the start of this whole thing, and then my wife and him figured out a way to cut this thing down into a chunk that is short enough. Okay, but the key point essentially is automation. Automation essentially is coming. Automation essentially we do it because we want to make our life easy. The real question is how can we certify what we are doing as automation systems? For that we need both a proper scientific methodology and a principled essentially approach to effectively build these systems. So I hope that I've given you sort of a tour of this and my own personal experience. The current situation is that it's just it's impossible to keep up with what's going on. It's very hard. But the point that I want to take everybody to take home is you need to find a way to be invariant to what's going on outside. So what does that mean? That means I think that you need to have a thread in the background which is preparing you with a portfolio of tools that you're constantly churning and then building up. And then you need to organize yourself in your own way, exactly what you know, what you don't know, and then how you think you want to go. And then use the essentially work in teams and work essentially in these groups and then move forward. So in other words, I think that the challenge essentially is we need to follow principles. We need to have principles. And principles will allow us to do this. That doesn't mean that it's laziness. You can't be lazy, really. Laziness comes when you do the action, when you do to really solve the problem. But before you can be lazy, you got to prepare. And you have to prepare a lot of background stuff. And you need grounding in science and in engineering. Thank you very much.
Thank you.